The first type of switching mode regulator is a buck regulator. In a buck regulator, the average output voltage, we denote that with VA, is less than the input source voltage Vs. Hence the name buck. In this circuit diagram, the buck regulator using a power BJT, as Vs is greater than the load average voltage, this is like step down chopper. The circuit operation can be divided into two modes. The first mode, when the transistor Q1 switched on at t equals to 0, the input current which rises flows through the filter LC and the load. In mode 2, transistor Q1 switched off at t equals to T1 or at t equals to KT. Freewheeling diode DM conducts due to the energy stored in the inductor, and the inductor current continues to flow through LC, load and diode DM. The inductor current falls until the transistor Q1 is switched on again in the next cycle. Depending on the switching frequency, filter inductance and capacitance, the inductor current could be discontinuous. These two are the equivalent circuits for mode 1 and mode 2. Between 0 and KT, a supply voltage is given, the output voltage will be equal to Vs. When the transistor Q is off, the output voltage will be 0 and again rise to Vs. The input current Is will be present when Q is on, that is in mode 1, and that will be from minimum values to maximum value. When the Q is off, Is will be 0. Q is on, the Is will be rising. Is minimum, this is Is maximum. The inductor current will start increasing during the turn on time and reaches the maximum value from the minimum value, and again starts decreasing to the minimum value during the mode 2 operation. Again in mode 1 operation starts increasing minimum to the maximum value. In mode 1, IC equals to IL minus I0. Here also IC equals to IL minus I0. We'll try to draw this IC later on. I0 in both the cases is equals to the IA, average value. That average value will be a constant value since this regulator operates in continuous conduction mode. Now IC, during the mode 1, the IL is I minimum and I0 is equals to I average, and this value is greater than I minimum value. So we'll be getting a negative value here. The second mode starts IL equals to I max and I0 is nothing but IA. This gives us a positive value. At the end of first one, it's maximum here. Now again it reduces to minimum value. This cycle is going to repeat. The V0 average is sinusoidal voltage. This is delta VC. VC is in parallel with the load. The load average voltage will be the average voltage of the capacitor. This will be sinusoidal since increase gradually and decreases gradually in case of a capacitor. These are the waveforms. Now the voltage across the inductor L, in general, that VL equals to L into di by dt. The inductor current rises linearly from I minimum to I maximum in the time KT or T1. In that time, the voltage is Vs minus Va, which is equals to L. Change in the current is I max to I minimum. The time T1, where T1 is the T on time or KT. Let this be equation number 1, from which T1 is given by L, I max to I minimum, which is nothing but change in the current, divided by Vs minus Va. Let this be equation number 2. During the turn-off period, that is T2, the inductor current falls from I max to I minimum, and the voltage is available is only average output voltage, that is negative, is equals to minus L delta I divided by the time T2. Let this be equation number 3. Then from which T2, or which equals to T of time, or 1 minus KT, where K is the duty cycle, is given by T2 equals to L delta I divided by V. Let this be equation number 4. Now, assuming the lossless circuit, then the input power Vs Is equals to the output power Ia Va. From equation number 5, Va equals to K Vs. So K Ia Vs. Now from this to Is equals to K Ia. That is equation number 6. Now the switching period T is equals to the 1 by the switching frequency, that equals to T1 plus T2. Now substitute these values from equation number 2 and 4. Then you will be getting delta I L by Vs minus Va plus delta I L by Va. Now T, that is 1 by F, is equals to Va of Vs minus Va, Va delta I L plus Vs minus Va delta I L. Take the common, that L delta I Va plus Vs minus Va divided by Va Vs minus Va. The switching period T is equals to 1 by switching frequency equals to L delta I Vs divided by Va of Vs minus Va. Let this be equation number 7. Now from which peak to peak ripple current in terms of switching frequency, delta I equals to Va Vs minus Va divided by L F Vs, right? Replace the term Va with KVS, KVS of Vs minus K Vs divided by L F Vs. Then K, take out the Vs again, so Vs square 1 minus K divided by L F Vs. Delta I equals to K Vs of 1 minus K divided by LF. That is equation number 9. Now using Kirchhoff's current law, that is KCL, and the inductor current IL equals to IC plus I naught. If you assume that the load ripple current delta I naught is very small and negligible, then the delta IL, the peak to peak ripple current of the inductor, equals to delta IC. Average capacitor current which flows into this capacitor current is present during the turn on T1 and during the turn off T2, so the average is by 2. That will give us this total T time by 2. Average capacitor current IC given by delta I divided by 4. Now the capacitor voltage VC is equals to 1 by C integral of I C of dt plus Vc at t equals to 0. The peak to peak ripple voltage of the capacitor C is given by Vc minus Vc at t equals to 0. That is delta Vc. Delta Vc is given by 1 by C, this integral 0 to t by 2 delta I by 4 dt. That equals to delta I of t divided by 8c. In terms of switching period, now in terms of switching frequency, which is nothing but delta I divided by 8c of F, equation number 10. Substituting the value of delta I from equation number 9 in 10. Now delta Vc equals to Vs K of 1 minus K by Fl multiplied by 8 Cf. Delta Vc equals to Vs K of 1 minus K divided by 8 LCF square. Equation number 11. The buck regulator requires only one transistor and has high efficiency greater than 90%. And the di by dt of the load current is limited by the inductor L. The input current is discontinuous and a smooth input filter is required. It provides one polarity of the output voltage and unidirectional output current. It requires a protection circuit in case of possible short circuit across the diode path. This is regarding buck regulator.